Hey guys, my name is Bharat Thapa, and my prospective research title is Atomic Layer Deposition of Hafnium Nitride and Zirconium Nitride Multilayers as an Observer Material for Hot Carrier Solar Cell. First of all, I would like to start with what a hot carrier solar cell is. It is one of the elegant approach or concept in so-called third generation photovoltaics, in which we try to maximize the efficiency of thin film solar cell devices significantly while reducing the manufacturing cost of the panel as compared to the first generation wafer-based silicon solar cells. Peta and the team in 2009 have calculated the maximum efficiency of a hot carrier solar cell operating in a practical condition to be around 50 to 55 percentage, which is far less than the theoretical thermodynamic and detail balance limit, but still 50 to 55 percentage is higher than any highest existing solar conversion efficiency. So far, 40% conversion efficiency, which was found in 2014 in UNSW, is the highest efficiency ever. So you can say that my research is focused on getting the higher efficiency at lower cost of the clean and renewable energy from the sun. Carrier solar cell, we try to minimize two intrinsic losses of a solar cell. Those are thermalization loss and the low band gap energy losses. So we have to engineer observers such that these losses are minimized in a hot carrier solar cell. And the other important component of a hot carrier solar cell is energy selective context, which is not my research topic. So let's focus on the observer. Nitrides of hafnium and zirconium are a good candidate for observer since they fulfill most of the requisite criteria to be an observer of a hot carrier solar cell. Since their constituent atomic masses are different by more than a factor of 4, a phonon bottleneck can be seen in them, which is because of the prevention of Clemens and Ridley decay of the optical phonon in their crystal lattice. This will cause the hot carriers, hot electron in this case, because mononitride of hafnium and zirconium are metals with zero electronic band gap, to remain at elevated temperature or at higher energy, so that they can be extracted by energy selective constant. We want this carrier lifetime in the order of a few nanoseconds, and this has been in fact shown in UNSW for both of these nitrides separately, yeah. And the only problem remained is the better deposition method and the further prevention of the phonon transfer for establishing a proof of concept in this material system. That's why I propose deposition of hafnium and zirconium nitride by atomic layer deposition. Atomic layer deposition is a versatile and highly renowned method for depositing high quality of material which are pinhole free, very pure, and very highly conformal. In atomic layer deposition, the reaction takes place between two gaseous precursors at the reaction chamber, and which produce desired deposition on a substrate. In fact, atomic layer deposition of hafnium nitride and zirconium nitride, both conducting and semiconducting, have been done in lab by different researchers, but those studies, the depositions were for different purpose. In my research, I am not only depositing zirconium and hafnium nitride monolayers, but I will also deposit multi-layers of them. Because it is because many studies have shown that the acoustic phonon, the mismatch between the acoustic phonon at the boundary layer prevent the transfer of heat dissipation, or the transfer of those acoustic phonons which manifest as heat dissipation in higher and macro level. So I hope, because of the acoustic mismatch, the heat loss will be reduced, which means better solar conversion efficiency and better performance. That's why I propose to deposit hafnium and zirconium nitride multi-layers by atomic layer deposition in my research. Thank you.